Hello. Today we will discuss structural loads. As an overview, we have to discuss a portion of codes, its symbols and notations used, dead load, live load, roof live load, wind load, and earthquake load. We normally use the American Society of Civil Engineers 7-16, the updated one for the minimum design loads for buildings and other structures. In international setting, we also use the International Building Code. For the design codes, we normally use the ACI, the Building Code Requirements for Reinforced Concrete. Also, we have the Manual of Steel Construction for the EIAC, and for highways, there is also for the wood construction and for the railway construction. In the Philippines, we use the National Structural Code of the Philippines. We call it the NSCP. This is the Bible of structural engineering in the Philippines. Also, aside from NACP, there is the National Building Code of the Philippines, the PD 1096 series of 1997, which the Office of Building Official are using. And also we have the Accessibility Law, or the BP 344. For the symbols and notations used in NSCP 2015, you can see all here like capital D as a dead load, A as the earthquake load, F as the fluid load, H as the lateral pressure of soil and water in soil, L as live load, L sub R as roof live load, R is rain load, W as the wind pressure. For the dead load, we normally look for the densities of the material that we are using. NSCP table 204-1 gives us the minimum densities for design loads from materials. This is in kilonewton per meter cube. So take note, it says minimum density, so you can actually assume a larger value than this, but you cannot go below this one. So you have to follow the minimum value. Like for example, for Lawaan, it has a relative density of 0.4, so it is quite light, 3.92 kilonewton per meter cube. For Molabi, it's heavier with a relative uh, density of 0.69, so the density is 6.77. For the Malabayabas, medyo bugat na siya. It's a heavy wood, so zero point 0.9 is the specific gravity. So the density is 8.833. So as you can see, I just give you the idea how are the densities of different woods from 3.92 to 8.83 kilonewton per meter cube, which is lighter than water. For the first water, we have 9.8 kilonewton per meter cube, and the seawater, 10.1 kilonewton per meter cube. Also, a common material, the clay and gravel, which is dry, is 15.7 kilonewton per meter cube. For a wet sand and gravel, 18.9 kilonewton per meter cube. So for a plain concrete, it will give us 22.6 kilonewton per meter cube, and for a reinforced concrete with the addition of the reinforcement, it will be heavier, so it's 23.6 kilonewton per meter cube. Normally, you will see some of the references they are using 23.56. Gi-run-off lang na siya to 23.6. But we normally do in practice, we use 24. It's easier to multiply that whole number. For a glass, which is heavier than reinforced concrete, that's 25.1 kilonewton per meter cube, and steel 77 kilonewton per meter cube. Or if you need more materials, you can look at table 204-1 for the materials, which is not mentioned. I just mentioned the common materials that we use in construction. Also, we have the minimum design dead loads for, like for example, the mechanical duct allowance. It's zero point 0.2 kilopascal. That's uh, Newton per meter square. Also, if you use the ceiling as gypsum board as a ceiling, the minimum design load is 0.008 per millimeter thickness of the gypsum board. If you are using for floor finish ceramic or quarry tile that is 20 millimeter on 25 millimeter mortar bed, uh, you will be using 1.1 kilonewton or kilopascal. For metal deck with 20 gauge, zero point 0.12, a plywood 0.006 per millimeter. So this is lighter than the gypsum board. Wood shingles 0.14 kilopascal. Frame partitions, which is movable 0.24 megapascal, kilopascal. Frame partitions, wood studs 500 by 100, plastered two sides. That's 0.96 kilopascal. For the partition load, NSCP says in section 204.3, floors in office buildings and other buildings where partition locations, take note, are subject to change shall be designed to support, in addition to all other loads, a uniformly distributed dead load equal to 1.0 kilopascal. So we will have a minimum partition load of 1.0 kilopascal, which usually happens in office buildings. An exception to this is an axis floor system shall be designed to support, in addition to all or other loads, a uniformly distributed dead load not less than zero point 0.5 kilopascal. So how do we do computations of the dead load? Uh, like for example, we have this given diagram, a plan of a floor plan. The dimensions of the beam is 300 by 500 millimeter with the thickness of the slab which is 100 millimeter, and the length of one span is L1 4 meters and the length of the other span L2, which is also 4 meters. So you can see it here in the section drawing. We assume that the unit weight of reinforced concrete is 23.6 kilonewton per meter cube. And if we put a floor finish, a ceramic or quarry tile 20 millimeter on 25 millimeter mortar bed, the value is 1.1 kilopascal. And assuming that a ceiling load is 0.48 kilopascal. So first is we need to determine the tributary width of the middle beam. So in this case, we simply take half of the dimension of L1, that is L1 over 2, and half of L2, L2 over 2. So we have to add these two dimensions, which will give us 4 meters. So we will call this one as the tributary width, and we have to multiply this to the corresponding quantities. First, we need to determine the cross-sectional area of the slab and beam to determine the what we call the self weight. Here, we took the area which is equivalent to 0.52 meter square, so that the self weight due to the beam and slab can be multiplied with the unit weight of the concrete, which is 23 kilonewton per meter cube times 0.52 meter square area. So look at the units. So we can cancel meter square at meter cube. So the remaining unit will be kilonewton per meter. So the self weight is 12.27 kilonewton per meter. The superimposed dead load, the additional loads which is not included in the self load, is due to the ceiling and the floor finish. We assume a floor finish of 1.1 and a ceiling of 1.48. So the total superimposed load is 1.58 kilopascal. Or you can directly multiply it with the tributary width, just like what I did here, by multiplying it by 4 meters. So the floor finish has a load of 4.4 kilonewton per meter, and the ceiling has 1.92 kilonewton per meter. So that the superimposed dead load is, you have to add 4.4 plus 1.92, that's 6.32 kilonewton meter. And the total dead load D is therefore equal to the self weight 12.27 plus the superimposed dead load 6.32. So the total dead load is 18.59 kilonewton per meter. So this is a realistic value. So when you are designing, you should be able to get around this value, or you can just use 18.6 or 18 point, or depende 19 kilonewton per meter, or pwede naman po 20 kilonewton per meter. It depends on you because you are the designer. At least you should not go below this one. Okay. Also, we have what we call a live load. Live load is a transient load, meaning it's not permanent, it's temporary. So we humans are live load. So with the furnitures, because furnitures are not fixed. So you can use table 205-1 as the minimum. Again, take note, minimum uniform and concentrated live loads. Here we have a uniform and a concentrated live load. You have to check uh, the effects of the uniform live load independently with the concentrated load. So, like for example, for a dining room or and restaurants, the uniform load should be 4.8 kilopascal with no concentrated load. So, medyo bugat na siya, 4.8. Here we have for an office category. Normally, for call centers, we use 2.9 kilopascal as the uniform load. And you also have to check using 9 kilonewton concentrated load. All of the other offices is 2.4. For lobbies and ground floor corridors, we use 4.8 kilopascal. For residential, normally we use the basic floor area, which is 1.9. For the decks, 1.9, and the storage also 1.9 kilopascal. But for the exterior balconies, because there is a tendency that there will be overcrowding, so we have a heavier uniform load of 2.9 kilopascal. For schools, the classrooms need 1.9 kilopascal with a concentrated load of 4.5 kilonewton. For corridors above ground floor, 3.8, much heavier. For ground floor corridors, 4.8 kilopascal. So to give you an idea on how to determine the floor live load, we simply multiply the given minimum load by the tributary weight. Since we have a tributary weight of 4 meters, again, looking back at the previous example, for residential building, we are using 1.9 kilopascal. Again, you need to quantify that one. 1.9 kilopascal, or that's 1,900 Newton per meter square. If just an rough estimate, you just have to divide it by 10 to determine or to convert that in kilograms. So 1,900 divided by 10, that's 190 kilograms per meter square. So probably most of the women have a weight of around 50 kilograms. So that would be around four of you to be standing around uh, 1 meter square. So that's how heavy the 1.9 kilopascal is. But normally in residential areas, usually kung gamay lang nga balay, duha tulo ra man gyud mo, di ba? So normally, aside from people, there is the furniture. So the code usually allows us to use half of the live load. So instead of 4 people, we allow 2 people in 1 square meter. But as of now, just follow this one. 1.9 kilopascal times 4, so 7.6 kilonewton per meter. For the floor live load in office, we have 2.4 times 4, 9.6 kilonewton meter. It becomes heavier. If we have a retail store, that's 4.8 kilopascal times 4, so 19.2 kilonewton per meter. And also, if we use a light storage that would be heavier, 6 kilopascal times 4 meter, which is 24 kilonewton per meter. Aside from that, we have the roof live load. Uh, Especially during construction, there will be loads in the roof, or even after construction for maintenance, there will be somebody who will be climbing above the roof. So as you can see, there are two methods, the method one and method two, and it depends on the roof slope. So also it depends on the tributary area. So if you have a slope which is flat or rise less than 1 unit vertical in 3 unit horizontal, that's around 33.3% slope. Uh, and if you have a tributary area around 40 meters square, so your uniform load is 0.75. And you can see the uniform load also in the method 2, 1.0 with the rate of reduction R and the maximum reduction capital R. Okay, so as you can see, the minimum roof live load is around 0.25 here at the awnings except cloth covered up to a maximum of 1.0. This is what I am saying earlier. The code actually allows us to reduce the live loads. The design live load may be reduced on any member supporting more than 15 meter square. So that's around 4 by 4 meters. It's irregular bedroom, excluding flat slabs, except for floors in places of public assembly and for live loads greater than 4.8 kilopascal. You can use this live load reduction R, which is equal to capital R is equal to the small r times A minus 15. Note that for storage loads exceeding 4.8 kilopascal, no reduction shall be made, except that design live loads on columns may be reduced 20%. Also, the reduction shall not exceed 40% for members receiving loads from one level only, 60% for other members, or R, as determined by the following equation. The live load reduction capital R is equal to 23.1 times 1 plus dead load over the live load. Take note that A is the area of floor or roof supported by the member, capital R, reduction of percentage, small r, rate of reduction equal to 0.8 for floors, and for others you can see table 205.3, the table that we have shown earlier for roofs. As an alternative floor live load reduction, you can use this equation. The L is equal to L sub O times 0.25 plus 4.57 times 1 over the square root of EI. EI is defined as the influence area. Take note that the influence area A sub I is 4 times the tributary area for a column, 2 times the tributary area for a beam, equal to the panel area for a two-way slab, and equal to this product of the span and the pole plans width for a precast T-beam. So here you need to determine first the tributary area for a particular structural member and then multiply it with the different multiplier to determine the influence area. Okay, so that's all for now. I will discuss in a different video the wind load and the seismic load. Thank you.